for the sake of simplification, we're going to make some assumptions. So first of all, trusses, we're going to consider them as bars connected by pins. Some other assumptions is that the members only support load along their length. I'll describe this later with an example. And there's not going to be any bending and deflection that we learned in the last lesson. We are also going to assume that there's negligible mass and friction. And another key thing is we're always going to assume equilibrium. So all the forces in the x, y are going to be equal to 0. So the main way we're going to be solving for these trusses is called the method of joints. There are 3 main steps to it. You're going to draw a free body diagram of your entire system, solve for the unsolved external forces. Then we're going to cut it up around the joints and draw free body diagrams around a certain joint, and we're going to be able to solve for all those trusses. The best way to probably learn this is going to be through an example. So here we have an example of all these trusses and the joints. I labeled A, B, C, D. We could see that the joints are connected through a pin and a roller. So let's get started. First, we're going to draw all our external forces that we have. So we have this F that's already been there. And now, if you recall from last lesson, in pins, we have reaction forces in the X and Y direction. So I'm going to call this AX and AY. And in rollers, we're only going to have reaction forces in the Y direction. So I'm going to call this BY. Solving for this, we're going to get that AX is going to be equal to 0. AY is going to be equal to negative F. And BY is going to be equal to 2F. So in the next slide, we're going to do the method of joints. We're going to apply this concept by cutting it up and applying it to a joint. So just for reference, we're going to be doing it along point A. Right here. And what we're going to do is we're going to isolate that point and cut it up. So this would be point A right here. We would have this force that we will call AD because it's AD. So we're going to call this upward force, force AD. And we also have this force, force AB. And we also have AX is going to be 0, but AY is going to be negative F. So it's going to be going down by F. As for directions, always just making it come out of the joint, and the signs will figure itself out later on. So I redrew the joints over here on the new slide so we have a nice fresh page. And now we're going to be looking at what we know and what we don't know. So things that we know the force going downward is going to be F right here. We also know the angle. We're going to assume that we know that. And the things that we're going to solve for is force AD and force AB. So the way we're going to do this is applying our equilibrium equations. So we know that all the forces in the x direction needs to be equal to 0. So let's look at what's in the x direction. We're going to make right positive. So we have force AB going to the right. And we also have force AD. The component is going to be cosine of theta. And that's all going to be equal to 0. In the y direction, we have the negative force. That is already unknown. And we also have force AD sine theta is going to be equal to 0. So now we could start solving for them. So here we could get that force AD is going to be equal to F divided by sine theta. And now we could solve for FAB. We're going to end up getting that FAB is going to be equal to negative F cosine theta divided by sine theta. So we're going to have to repeat this process for all the joints. So let's look at joint D. So at joint D, I redrew the free body diagram right here. Things that we know F, we know theta, and we also know FAD. We saw that when we did method of joints for point A. And we know FAD equals F over sine theta. So again, we're going to start with our equilibrium equations. And maybe things to point out is that this is going to be equal to theta, and this is also going to be equal to theta. Kind of hard to see. I apologize for that. So we're going to end up getting, so let's write our equations out. We're going to get that FDC is pointing to the right plus FDB cosine theta minus FAD cosine theta. That's all going to be equal to 0. We're also going to get the FAD, negative FAD sine theta minus FDB sine theta is also going to be equal to 0. So we have 2 unknowns and 2 equations, so that's a good sign. So the things that we don't know are going to be FDC and FDB. So we could solve accordingly, and what we're going to end up getting is that FDC is going to be equal to 2f cosine theta divided by sine theta, and FDB is going to be equal to negative f divided by sine theta. So now we're going to do the method of joints at point C. So the things we know force, theta, and we know FDC from our previous joint solving. So now we could solve for FCB. Because we only have one unknown, we only really need one equation. So in this case, I think it's easier to do it in y, but you could also do it in x. So force in y equals 0. We have that negative force coming down minus the force CB multiplied by sine theta. And what we're going to end up getting is that FCB is going to be equal to negative f sine theta. So I just want to make one final point, is people sometimes ask, like, why don't we solve for joint B? And one thing I want to tell you is to be very smart about your time and what you're solving for. So these are all the things we solve for. So the best way I think to look at it is I could eliminate which ones I've already solved for. So I solved for force AB, I solved for force AD, I solved for force DC, I solved for force DB, and CB. So I solved for all the trusses. So that means I don't really have to do joint B because I already solved for everything. So be smart about your time, solve for what you need to, and don't be repetitive. So this is our final section on structures. So for our project, we're going to be doing a marshmallow tower. And what we're going to do is we're going to build our own structures, and we're going to place a marshmallow on top. Just be ready to be able to solve for trusses. Trusses can be really complicated, especially when you have a lot of factors and trusses going through them. But just make sure to take it step by step, focus on each joint, and you'll be able to do this. You got this.